Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 95. It's on the center of mass. I want you to take a look at this tire for a second, and I'm going to apply a force to it. You can see the motion is fairly regular, and the reason why is that the center of mass is right in the middle of that tire, and it's rotating around that center of mass. Now let me apply a force to a hammer, and you'll see that the motion is not as uniform. It's tricky to our eyes, and the reason why is that the center of mass is off-center. What I'm going to do, though, is keep the center of mass where it is, and then I'm going to rotate that hammer, and you'll see that the center of mass stays where it is. It's just the motion of that object above and below the center of mass that fools your brain. Now let me show you a system. So this is a Saturn V rocket. It's made up of a number of different stages. And so where would you say the center of mass is, the average mass? Well, it's maybe somewhere like that. What do you think would happen to the center of mass if I were to break this rocket apart into its two stages at this point? Well, it will stay in the same location. And so if we don't have an external force acting on the system, the center of mass stays where it is. Even though that might be rotational motion as we break those stages apart, the center of mass remains where it is. And so any system is going to have a center of mass, and that center of mass is made up of all the objects within the system. And what's neat about physics, according to Newton's second law, is if we don't apply a net external force, then there's going to be constant velocity. In other words, we're not going to have acceleration in that object. It'll either remain still, the center of mass, or it's going to move with a constant velocity. And so how do you figure out where the center of mass is? Well, a good place to get started is with a simulation. And this is Center of Mass Builder from SimBucket. And what you can do is you can click on the screen and it starts to make mass. It'll then show you where the center of mass is. So you can see if I make a uniform mass, center mass is right in the middle. What happens if I add another uniform mass in the x direction? It's right between the two. What if I move in the y direction? You can see that it's going to be the average of that as well. So the center of mass doesn't have to be within a specific object. What's neat is you can use the hang test in physics. So if we simply hang this object, if we let it settle out, the vertical line through that hanging point is going to go right through the center of mass. So you can calculate the center of mass experimentally, and I'll show you how to use an equation to do it a little bit later in the video. And so if we apply a force to an object, we can get what looks like irregular motion in this hammer, but since we've applied a force, we know that we're going to have constant velocity. And so if I mark where that center of mass is, slow it down, watch what happens, we're going to have constant velocity. And that movement above and below that center of mass is confusing to our brain. And so let me show you how this works with a little video. I've got two pieces of ice that are connected together with a spring. I'm going to apply a force to one and they're going to slide across the ice. And so we get this caterpillar-like motion. So to our brain, it looks like we're having acceleration and deceleration. But what I want you to do is get involved. So I want you to hold your finger on the screen where the center of mass is as I play this video. Where would that center of mass be? It's going to be on the spring right between those two blocks of ice. And so what you're going to try to do is, as I play the video, keep your finger between the objects on the spring. And so let's do that. So you should be tracing it out. Keep your finger between the blocks. And you should find that as you trace it, you're showing movement from left to right with constant velocity. It's slowing down at the end a little bit. Now let's try a little harder one. We've got a force on both of these bricks on either side. So again, what you're trying to do is hold your finger in between those two bricks on the spring itself. So let me play this video. And I'm doing this as well. So what I'm finding is that it's not moving as quickly, but it's still moving with constant velocity from left to right. And we could do even a complex system like this. We have 4 objects that are connected together with springs. So try to hold your finger where the center of mass is. That's going to be between all 4 of these objects. And if you do that, it's hard to kind of keep it in between all 4, but your brain's pretty good at this. Again, what am I finding? There's crazy motion on the screen, but my finger is moving across with constant velocity. And that's because there's no external force. And so we could look at a rocket. As a rocket flies through the sky, it takes a parabolic path like that. So we could trace it out and it would look like that. But let's say we were to take that same rocket and it were to fly through the sky, but halfway through it were to break apart into its two different parts. So it looks odd. In other words, that motion looks odd as it breaks apart. But if we were to plot the center of mass, it would follow the same parabolic path that that rocket by itself. And that's because we have no external force. And so what's neat about the center of mass is you can take systems that are incredibly complex, and if we just figure out where the center of mass is, it makes solving that problem much easier. So as you move into AP Physics 2, you'll have to calculate where that center of mass is. And so if we have this object right here, so we have two masses, they're connected with a bar, but let's say there's no mass in that bar. Here's the formula that shows you how to calculate where the center of mass is. And what you do is really find the point where you could balance that object on that point. And so we set up an arbitrary distance, a distance away in the x from our object, and we'll call that xcm. That's going to be the center of mass. We then set up our two distances. This is going to be x1. It's the distance to the center of mass 1. And then x2 is the distance to the center of mass 2. So our formula, all you do is simply multiply mass 1 times x1. So it'd be this mass times that x, plus this mass times that x, and then you're dividing the whole thing by the sum of the two masses. In other words, mass 1 and mass 2. So if I give you a problem, you could pause the video at this point and try to solve it, but I'll show you how to work this one out. And so what you would do is you would simply multiply mass 1, which is 1 kilogram, times the distance, which is 2 meters, plus mass 2, which is 2 kilograms times the distance of 5 meters, and then you divide it by 1 plus 2 kilograms, or 3 kilograms. So if we set up it looks like that, and you should get a distance of 4 meters. In other words, xcm is going to be 4 meters from here. And so it would be 2 meters from mass 1 and it'd be 1 meter from mass 2. That's a pretty easy problem. But if you could throw in different values, then you're going to get a harder problem. What if I throw in another mass like this? How would you solve it? Now we have 3 masses and they're moving in the x-axis. All we do is simply add this. Mass 3 times x3, where x3 is the distance to the center of mass 3, and then we're going to divide by the sum of all 3 masses. And so solving it, you could have 12 masses. It's pretty easy to figure out where that center of mass is. What if I were to turn it like this? Instead of going in the x, it were also to go in the y. Well, how would you do this? First of all, we would have to get the x coordinate of the center of mass, so we're going to use this formula down here. You would then choose an arbitrary distance in the y, and then you're going to use the same equation, but this time instead of figuring out how far we're going in the x, you'd also figure out how far we're going in the y. Now I know my x coordinate, my y coordinate, and we could even move into the z to figure out where that center of mass is. Remember, if we don't apply a force to it, it's going to have constant velocity, and then as you move into AP Physics 2, you have to be able to calculate in 1 and 2 dimensions where that center of mass is. So I hope that made sense, and I hope that was helpful.